Welcome back, everybody. In chapter 2, we're going to start talking about probability. All right. But before we get started, I do want to talk about just a few quick definitions to make sure that when I use a certain term, that you guys were all on the same page and you know what I mean. The first is the term probability experiment. All right, and a probability experiment is a process that leads to a well-defined result. All right, and that well-defined result is called an outcome. So the next term is outcome, and we'll say is the result of a single trial of a probability experiment. All right. The third term I want to talk about, and this one is probably the most important, is called sample space. All right. Sample space is going to be used a lot. And a sample space is the set of all possible outcomes. Of a probability experiment. All right. And the last term is event. An event consists of outcomes. All right, so let's talk about the term sample space for just a minute. So I'm going to have a couple of experiments here. Experiment and sample space. So the first experiment we have is tossing a coin. And the sample space for tossing a coin is you either can get a head or a tail. So your sample space is either head or tail. If your experiment was rolling a 6-sided dice, the sample space would be 1, 2, 3, 4, 5, 6. All right. If we decided to toss 2 coins, right, then your sample space would be a little bit different. All right. We could get, if we toss 2 coins, it could be head, head. It could be head, tail. Could be tail, then head. Or it could be tail, tail. Actually, I'll make 2 T's better. Tail, tail. So your sample space is going to be different depending on the probability experiment that you are doing. All right. Now your sample space doesn't always have to be small. All right. Your sample space could be larger. For example, if you rolled 2 dice, you would get a very large sample space of 36 different outcomes. All right, and the way to manage such a large sample space would be to make a chart, and you'll find that I like making lots of charts. I'm going to start the chart for you, let you finish it up. There's die 1. There's die 2. For die 1, the sample space is just 1, 2, 3, 4, 5, 6. For die 2, it's 1, 2, 3, 4, 5, and 6. And when you roll 2 dice, you're going to get 2 different numbers. So for example, if I rolled a 1, right, I can roll a 1 and a 1. I could roll a 2 and a 1. I could roll a 3 and a 1, right? 4 and a 1, right? So as long as my roll on die 2 is a 1, I could have 6 different potential rolls. Now when die 2 becomes a 2, we get a whole different story. So I can get like 1, 2. I can roll a 2 and a 2. I can roll a 3 and a 2, and so on and so forth. So this is just an organizer. It's just a way to organize your sample space so then you can do some things within it. Why don't you pause the video now and try to run out the string on your sample space, write in the rest of these, and when you get back, we're going to move forward. All right, so hopefully you were able to fill in that chart. I did start it for you, so the filling in is just more of a activity to finish out what we all started together. I do want you to give you a chance to try a sample space on your own. So here's the situation. We're going to write out a sample space for the gender of children if a family has 3 children. All right, we're going to use B for boy and G for girl. So why don't you pause the video once again and take a shot at writing out this sample space on your own. We'll do it together when you come back. All right. So the first possibility is that the family could have 3 boys. All right. They could have a boy, and then a girl. They could have a boy, a girl, and a girl. Or they could have a girl, a boy, and a boy. And that's possible. Now, are there other possibilities? Absolutely. Right? We tested all the possibilities, right? We have 3 boys, we got 2 boys, we got 1 boy, right? But if we had 2 boys, we could have our 1 girl in multiple spots. We could have the girl come first. We could have the girl come last. We could also have the girl come in the middle. Yes? So we could have boy, girl, boy. But now we could have 2 girls, so we could have girl, boy, girl. We can have girl, girl, boy. Or we can have 3 girls. Girl, girl, girl. All right. And how many? 1, 2, 3, 4, 5, 6, 7, and 8. All right. So we have our 8 spots. Take a double check to make sure that every possibility has been taken. We haven't left any stone unturned. There is no possibility for having 3 children that we haven't taken into account. And this is what we call sample space. All right. Later, we will determine a way to figure out, a quicker way than writing it out, to figure out how many outcomes should be in your sample space. But for right now, writing it out just seems fine. It helps with practice. All right. All right, so let's talk about some counting techniques. So this is section 2.2, right? Counting techniques. And the first thing we learn about is the fundamental counting rule. Now this has a very mathematical explanation. It's not one that's easily able to be understood. I kind of like using an example to illustrate the fundamental counting rule. All right. So let's say you own a sandwich shop, and you have, let's say in your arsenal, you have 3 types of bread. Right? We have 2 types of meat. We have 3 types of cheese. And we have 4 types of condiments. All right. So here's the thing. With so many possibilities, all right, writing out the sample space seems like an awful lot. And I'll just kind of give you a quick illustration that the sample space is going to get very large very quickly, all right? So let's say we start with our guy's here, and we have 3 types of bread. So here's 1 type of bread, 2 types of bread, 3 types of bread. Now with this first type of bread, we could have 2 types of meat, 1, 2. With the second type of bread, we could have 2 types of meat. With the third type of bread, we could once again have 2 types of meat. All right. Now, each type of meat can have different cheeses. All right. So I'm going to change colors just to help us out. 3 types of cheese. 3 types of cheese. 3 types of cheese. And so on and so forth. So the goal here is to see how many sandwiches we can make, right? Well, I haven't even gotten through the whole list, and I'm looking at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I've got 18 types of sandwiches, and I haven't even gotten to the end. All right? So, statisticians said that, amazingly enough, if you write out, this is called the tree diagram, by the way. If we write out this tree diagram, right, it fell into a pattern. And the pattern basically said, if I take the 3 types of bread and I multiply times my 2 types of meat, and I multiply times my 3 types of cheese, and I multiply times my 4 types of condiments, it's going to equal the same number of sandwiches than if I wrote out the sample space, or if I made that tree diagram. So why don't you guys multiply this out for just a minute, and I'll give you the answer in about 10 seconds. All right, so I got 72 different types of sandwiches. All right, and what you notice here is that this tree diagram is getting very large very quickly, very hard to draw, very hard to keep track of. But if you use this multiplication rule, basically, you can get the same number of sandwiches, and it takes not nearly as long. All right, so let's move on to the next example. All right, so here's the next example. At a gym, the locker combination code is 4 digits. The first digit must be a 0 or a 1, and the last digit must be prime. How many codes are at this gym? All right, well, if the first digit must be a 0 or a 1, that means for the first digit, there are only 2 possibilities. Now, for the next 2 digits, all right, it could be any digit between 0 and 9. Now, if you count the digits between 0 and 9, there are 10 possibilities. So the next two digits could have 10 possibilities. Now, the last one can only be a prime number. All right, so what we're looking for is between 0 and 9, how many prime numbers are there? And we have, I'll use green for my scratch work. We have 2 as a prime number. We have 3 as a prime number, 5 and 7. All right, 1 is not a prime number, so we cannot include that. So there are 4 possibilities. All right, and basically what we say is that the fundamental counting rule says if we just multiply these together, we'll get the same number as if we wrote out the sample space. When we multiply these, 4 times 2 is 8, 10 times 10 is 100, so it looks to me like 800 possible codes. All right, so the next thing I want to talk about is something called random selection. Now, you're going to hear a lot about this. Random selection is very, very difficult to define because there's a lot of people that say nothing is truly, truly random. All right, so we're going to define it as choosing an item without bias. All right, choosing an outcome without bias. All right. Some people will also say choosing, right, using a system that is equally likely, right, to get an outcome would be random selection. I like without bias because, you know, it's very difficult to prove equally likely. Like I said, definitions differ, but they all come out to be kind of the same idea, that if you're choosing without bias, that all possible outcomes are equally likely. The classic example most people give is when you're talking about rolling a dice, right? If you're just rolling the dice and you're not trying to bounce it off something, you're not trying to, you know, do it sidearm or get some special number out of it, or the dice isn't loaded, I would say all the numbers are equally likely, or you're choosing a number without bias, because whatever number comes up is the number you're going to choose. All right, so I did want to just touch on that real quick, but now I want to go into something that you probably haven't seen before, and that is the symbol factorial. And some people might have seen it before, but a lot of you probably haven't. And what you might see is you might see something like this. You have the 5, which you all have seen. The factorial symbol is simply an exclamation point. And what this means is take the number 5 and multiply it times all the numbers that come before 5 down to 1. So 5 factorial would be 5 times 4 times 3 times 2 times 1. If I had 3 factorial, it would be 3 times 2 times 1. If I had 7 factorial, it would be 7 times 6 times 5, 4 times 3 times 2 times 1. All right. Now, the reason you need factorials here is because we're going to deal with the concepts called permutations and combinations. All right. And let's define what those are. So permutation all right, is how many ways can we arrange objects where the order matters. Where order matters. All right, and where order would matter would be if you're in a club and you're choosing, let's say you have 20 people and you want to rotate your offices. So you have president, vice president, and treasurer. So you say, how many ways can we fit 20 people into those 3 offices? In that case, the order is going to matter because if you're president of the club or you're treasurer of the club, right, you have different duties and different things to do. All right, so if let's try an example. Let's show an example real quick. So let's say a business owner has a choice of 5 locations, right? But only wants to rank the top 3. In this case, the order is going to matter because business owner is looking to relocate his business. He's ranking the top 3. He's not just picking 3. He's ranking them first choice, second choice, third choice. I certainly hope that the real estate broker that's helping him out wants their property to be his first choice. All right. So in this case, there is a formula that is attached. So for permutations, we have N is always your total number of outcomes. P means permutation. R means the number that we're choosing. All right. And it's N factorial over N minus R factorial. So in this case, all right, I'm going to show you, we can potentially do this problem 2 different ways. All right. We're going to do it with the permutation formula. So if I have 5 total choices and I'm going to use a permutation because we said the order matters, you want to be that first choice. And we have 3 potential choices, right? So that means anytime I see an N, I'm putting in a 5. Anytime I see an R, I'm putting in a 3. So I have 5 factorial over 5 minus 3 factorial. Now, when I simplify this, I wind up having 5 factorial over 2 factorial, which means 5 times 4 times 3 times 2 times 1 over 2 times 1. All right, I eliminate those, and I wind up with 5 times 4 times 3, which equals 60. So there are 60 possible ways that we can rank 3 properties, right, if we saw 5 of them. All right. So let's move to the other idea. Oh, I did say I would do it possibly 2 different ways. Now, the second option is, right, there's my first choice, second choice, third choice. Let's use the fundamental counting rule to see if we can confirm our answer. So I just saw 5 properties. So how many do I have to choose from to give the real estate broker my first choice? There are 5 possible properties, right, of which I can choose from for my first choice. Once that first choice is logged in, right, I can't choose it again, really, right? So I have 4 potential properties for my second choice, and I have 3 potential properties for my third choice. And what we see is if we use the fundamental counting rule, 5 times 4 times 3 is indeed 60 possible ways to arrange this. Okay. So let's get into combinations now. All right. So combinations. Now, combinations are the same idea. We want to find the total number of ways to arrange something, but here's the difference. In this case, the order does not matter. All right. So here's the formula. Very similar, it starts out. However, right, there's a little extra with it. let's get right into an example. All right. In a club, all right. So let's see. Hang on. Let me get that example. All right, here we go. In a club, there are 7 women and 5 men. A committee of 3 women and 2 men is to be chosen. How many different ways can the committee be chosen? All right, so the reason I know this is a combination is there's no hierarchy on this committee, right? We're just choosing people, right? You 3 women, you're on the committee. You 2 men, you're on the committee, right? There's no president, vice president, secretary. There's no leader, right? Everybody's equal. Therefore, the order does not matter, which means that we are using a combination. So we're going to need actually 2 in this one. We need 1 for women, and we need 1 for men. And men is going to be out of 5. Hang on. We're choosing 2. So now we are going to execute the formula. So I have 7 factorial over 4 factorial, 3 factorial. And you can go back and check. I am following the formula. And we have 5 factorial over 3 factorial, 2 factorial. All right. So why don't you guys pause the video for just a second. Work this out. All right. I like to work it out on paper and then use the calculator as a finisher if I need it. But you do what you need to do, and we'll work it out together in just a minute. All right. So it's 7 times 6 times 5 times 4 times 3 times 2 times 1 over 4 factorial is 4 times 3 times 2 times 1, right? And 3 factorial is still there. So this and that, right, top and bottom, they all go away. So I'm left with 7 times 6 times 5 over 3 times 2 times 1. Now, I'm going to switch colors just for a second because we've got some things we can cancel here, right? I've got 3 can go with the 6, and I'm left with a 2, and then the 2 and the 2 can go. So I'm actually left here with 35 different ways we can choose the women. All right, so for the second one, I have 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1 times 2 factorial. Now, I'm just canceling those. So I'm left with 5 times 4 over 2 times 1. And I'm going to use the same green so the 2 can go away with the 4 goes 2. And I'm left here with 10 possible ways to choose the men. So the different ways to choose the women and the men use the fundamental counting rule. We have 35 times 10, which equals 350. All right, kind of a long lesson. There's a lot to do in here. I would definitely recommend rewatching the video if you need to, but there's going to be a lot more practice ahead. So thanks for listening, and I'll see you all next time.